Hello, everyone. Welcome to the ERI, or the Fall Environmental Resilience Series, jointly presented by IU's Integrated Program on the Environment and the Environmental Resilience Institute. Before we start, I'd like to make the following statement. Indiana University wishes to acknowledge and honor the Miami, Delaware, Potawatomi, and Shawnee people on whose ancestral homelands and resources Indiana University was built. So both IPE and ERI are founded on the understanding that interdisciplinary learning and research are essential to teach today's scholars and to solve today's problems. IPE is dedicated to bringing together all of the environmental and sustainability scholarship across the various schools and departments on the Bloomington campus. IPE is made up of over 120 faculty and nearly 1,000 students studying the environment from all angles, the sciences, arts, and humanities across more than 25 degree programs. ERI was founded in 2017 as part of the IU Prepared for Environmental Change Grand Challenge. Its mission is to enhance resilience to environmental change in Indiana and beyond by accurately predicting impacts and effectively partnering with communities to implement feasible, equitable, and research-informed solutions. So I'd like to thank, first I'd like to thank Sarah Mincy from IPE and Mariana Keynes from the O'Neill School who helped organize the seminar speaker series. We've had a wide variety of speakers over the course of the semester, and we have more to come. And our speakers are sharing their experiences, research, and insights with us. In particular, our speakers will focus on topics relevant to the issues of systemic racial inequality, environmental injustice, and the need for a just transition to a future that is healthy and safe for all people, not just those who have been privileged by centuries of inequitable systems and societies. You'll be able to find more information about each talk on the ERI and IPE websites. And you can also sign up for regular newsletters. So we encourage you to sign up for our newsletters so that you can get reminders about these upcoming events. So please be sure to keep your audio muted. And whenever you have questions, as you think of them, type them in the chat box. And we'll monitor the chat box throughout the talk. And there will be an opportunity at the end for questions to be answered. And those will be directed to the speaker from our moderator, Heather Reynolds, who is now going to introduce our speaker today.
Hi, everybody. It's great to be here with you today. I am delighted to introduce Dana Habib. She is an assistant professor currently in the Department of Informatics here at IU's Luddy School of Informatics, Computing, and Engineering, otherwise known as SAIS. Dana was trained as an architect and urban designer. I love this. She has master's degrees in city and regional planning and in architecture, as well as a PhD in city and regional planning. These all come from the Georgia Institute of Technology. And her research explores how climate responsive design interventions can help to mitigate climate change and improve the health of individuals and communities. And we have been really fortunate to have her as a member of the Prepared for Environmental Change Grand Challenge Working Group in Urban Green Infrastructure, where she has been mapping local climate zones to better understand people's heat exposure in Bloomington and Indianapolis, as well as mapping green stormwater infrastructure and developing an edible tree map for Bloomington. So with that, I'd like to turn it over to Dana.
Thank you, Heather, so much for that introduction, and welcome everyone. Thank you for being here today. I'm going to go ahead and share my screen with you all. Great. Can everyone see that? Wonderful. So thank you all for being here today. Today, I'm going to be talking about extreme heat vulnerability and what we can do to protect and empower communities. In this talk, I'm going to go over three main topics. I'm going to first talk about work that we've done with heat wave trends. Then I'm going to talk about different types of mitigation strategies that we can use at the local level. And then I'm going to talk about some more recent work that I'm doing with sensing technology. I'd like to start with the discussion on extreme heat and public health. We see that in the United States, more people die to extreme heat than any other form of natural disasters. On average, we can see upwards of 1,300 people who will die to extreme heat per year in the United States on average. And we can look at historical heat waves, such as the European heat wave of 2003 and the Russian heat wave of 2010, to see some of these examples of extreme heat waves, where in each of these events, over tens of thousands of individuals lost their lives during these individual events. These two heat waves rank among two of the deadliest natural disasters in the past century, and it really illustrates the importance of extreme heat to public health. We see that cities are more vulnerable to extreme heat because of what is known as the urban heat island effect. And the urban heat island effect occurs when we see temperatures in cities are higher than in their surrounding rural area. This temperature differential is due to basically how we are designing cities. We are displacing the natural vegetation in cities and replacing them with impervious surfaces such as roads, parking lots, and buildings. And all that impervious surface goes to raise temperatures in urban environments. But one thing that we don't just see a distinction between urban and rural and temperatures, but we actually see that temperatures vary dramatically within a city, and that we see a lot of different microclimates. And as Heather brought up, some of the work that we're doing with the urban green infrastructure is mapping local climate zones. What urban climatologists have found is that there are different types of microclimate zones that really impact temperatures. And so we can expect that temperatures are higher in downtown areas than they would be in a more residential area. And so, for example, we can see this variation. This is some work that I did last year looking at temperatures on campus. And we can say on a day of September that between Leading parking lot on unused campus and Dunn Woods, we see an 8.5 degrees difference in these two areas, which are pretty close together. So not only do we see that cities are consistently higher than their rural areas, but we also see that temperatures in cities are actually increasing at a faster rate in rural areas. And some of the work that we've done has found that actually urban temperatures are rising at double the rate of the planet as a whole. Cities are even more vulnerable to extreme heat because of this increase in trends. And then cities are more vulnerable because of what we're seeing with climate change. In the past 5 years, we have the hottest years on record. So 2016 still the hottest year from start to end. And as you all know, this has been definitely a trying year for climate change, where we really have it on the forefront of our mind. So I'd like to transition into some of the work that we're doing with heat wave, that we did with heat wave trends. And so with looking at extreme heat in cities, I really wanted to investigate how are heat waves changing specifically in cities. And so to do this work, I looked at the five largest US cities across the United States, and I tracked heat wave changes over 50 years. When tracking these heat wave changes, I defined extreme heat events based on Gavin and Ross' definition that extreme heat event is any day in which the apparent temperature exceeds the 85th percentile of the long-term temperature average of a particular location. The phrase particular location is really important here because we are using the local climate trends for each MSA to base on these EHEs. And that's really important when looking at health effects and determining what is an EHE. We used apparent temperature, was a combination of temperature and humidity, because we know that humidity really impacts our body's ability to cool itself, and is a better measure, apparent temperature is a better measure of heat stress. We used the National Climate Data Center heat stress index for the temperature, and we specifically were looking at daily minimum apparent temperatures, minimum referring to high nighttime temperatures. And we define heat waves as any two consecutive events, EHEs that lasted 2 days. We're really interested in looking at specific heat wave characteristics. And so what we would see is that we expect that heat waves that lasted longer would have a stronger impact to health effects because it doesn't allow for people adequate recovery periods. Also, we see that heat waves that occur early in the year also impacts public health and mortality effects because it doesn't give a person's body's ability to acclimatize to these higher temperatures. So we actually see a huge impact to mortality at the beginning of heat wave seasons. So we wanted to track how heat waves were changing with regard to the temperatures. And we're also defining them with minimum temperatures, these high nighttime temperatures, because minimum temperatures have been shown to be a better association with negative health effects due to extreme heat. And this is also important for cities because we see that minimum temperatures are amplified in cities because of the urban heat island effect. So what we find from this analysis is that we see that all 4 heat wave characteristics of frequency, duration, season, intensity are increasing across the United States over the 5 decades. We see that heat wave frequency, for example, is increasing by 20% each decade on average across large cities in the US. We didn't just look at this on average across the US, we actually looked at the individual trends for each of the cities. And one thing that we did was we grouped our cities into what we called vulnerable cities. And a vulnerable city was any city that had a heat wave heat wave characteristic that was increasing at a faster rate than the average United States. And you had to have an increasing rate above the US standards in at least 2 heat wave categories. So these are a list of our vulnerable cities that we identified. And so we can see that the cities are pretty distributed throughout the United States, really showing that no matter where large cities are located, cities really need to be planning for extreme heat. Also, one thing that we noticed is that cities on this map, especially when we did this analysis, that weren't considered hot cities were popping up as vulnerable cities like San Francisco and Portland. Los Angeles, which this year has had record heat waves, which were unprecedented. And so even during the study, we're already picking up these vulnerable cities. San Francisco was ranked as a vulnerable city and with regard to 3 heat wave characteristics, timing, frequency, and duration. And San Francisco had the fastest growing heat wave season of all cities in our study. And so, for example, heat waves in San Francisco were starting in 1960 by the middle of July. And by the end of our study, we're seeing them start by the beginning of June, the end of May, a month-and-a-half increase in heat wave season. And so this work that I did looking at heat wave trends I worked with the EPA to actually recreate this methodology and extend it to present day and to keep this work being updated to turn this into a climate change indicator. And so we worked on the data I'm going to be presenting today, is specifically ones where we extended out to 2018. And we didn't just do minimum temperatures, but we added maximum temperatures to look at the different definitions of heat waves. And we did a subset of the analysis as well to look at 1988 to 2018, because in a future work that we're working on now is that we want to look at urban growth and understand the correlation between urban growth and urban heat islands with regard to the change in heat wave trends. Some cities change in the analysis due to data availability. We see this is our data that we had before, and that we see when we add our next decade, approximately the next decade, we can see this continued increase in our trends, with the biggest difference within heat wave frequency and heat wave season. That's with season, we see on average a 16-day increase on average across all cities in our study for heat wave season. And so we see how now what's considered hot in our urban areas, the time of day is really starting to change. This is a map showing the different cities in the study that we're looking at, with the graduated symbol representing the change rate, the cadal change rate for each of the heat wave characteristics of frequency and season. And so we also looked at this with regard to minimum and maximum. So here's a slide where we put the two next to each other. And so we see the minimum in blue, the maximum in red, and we can see there's not as clear of a pattern as we saw with minimum with regard to maximum. But when looking at specifically the frequency and season, we see a much clearer relationship between minimum, and we're looking at the last 2 decades, and especially that we're really seeing that minimum temperatures may be starting to outpace maximum temperatures, or heat waves when defined as maximum temperatures. And so this is important for two reasons, is that we see this difference. One thing that we want to tease out, as I noticed, is this difference between minimum, maximum, and how we're defining temperatures, whether we see that this difference might be caused by urban heat islands. So we see the synergistic effect between urban heat islands and heat waves, and that this is increasing the vulnerability of cities to heat waves and to climate change. One other thing is to note is that there's no consistent heat wave definition. One of the studies looking at did a large literature review on different heat wave definitions and metrics used in research had shown that studies use different threshold values, different temperature metrics, different meteorological variables. And so there's no consistent heat wave definition at any level. And so as we can see, depending on how we define a heat wave, whether by minimum or maximum, we can actually see different trends. And some research is also showing that depending on how you define them, you see different impacts to mortality as well. And so one thing that I noticed when doing the literature review for this paper that we're writing is that we see that of the 16 heat indices examined, only 2 of them use minimum temperatures. And so minimum temperatures is being overlooked as an important metric to be used. Minimum temperatures are important for defining extreme heat events because they've been shown to be a better association with negative health effects. When looking and examining the heat wave of 2003 in Europe, researchers found that minimum temperature is one of the biggest drivers for extreme heat related mortality in Paris during that 2003 heat wave. Also, researchers looking at the difference between Europe had a heat wave in 2003 and then another large heat wave in 2006. Comparing these 2 heat wave events and comparing the mortality between them as well as the meteorological conditions, a lot less people died in that 2006 heat wave, even though maximum temperatures were very similar and sustained in the same way. People argue that this could be because the community was better prepared, because Europe definitely was not prepared in 2003, and so they were better prepared. But also a big difference meteorologically was that the minimum temperature was different, one of the main climate differences between these 2 heat waves. And so this is a discussion we want to bring up, is the importance of knowing how to define our extreme heat events, and also to try to make a standard that can be used for people consistently across the United States. And so the EPA has taken this heat wave trends and they have released it with the US Global Change Research Program. And now it is one of 16 climate change indicators used for the United States. And so you can see it down here in the bottom. And so this is important because we want our cities to be able to plan for climate change in cities. Not all cities have the resources to do climate projections or trends analysis, and so, or to run big modeling programs. But what the EPA is doing is releasing the methodology. They're in the process of releasing the methodology and the access to publicly available data. And so now 189 cities across the United States have access to this data as well as the methodology so that they can plan for climate change trends in their specific city. And so that's one thing that I think is really important for us when thinking about how we can prepare, is to understand our risk to climate change and to extreme heat. And the climate change indicator is one way that cities can start doing that. And so what else can we do to plan events and heat waves? And so what we're seeing in the that cities can do is that they can prepare emergency response plans. And so they can look at staffing and make sure that we have appropriate staffing during what really is the heat wave season, and look at infrastructure resilience and public education, and include infrastructure for extreme heat, such as cooling centers, especially for vulnerable populations. But cities can also manage their ambient heat. So one of the research studies that we did, we examined all climate action plans for the largest 50 cities. And when we did this review, we noticed that 9 in 10 US cities were pursuing policies to reduce greenhouse gas emissions, but only 1 in 8 were pursuing policies designed to manage ambient heat. And this is an opportunity for cities. And so what it means to manage ambient heat is to manage the urban heat island effect. And we have specific strategies that we can use. We can do albedo strategies, and albedo strategies are where we are changing the reflectivity of surfaces. example of their cool roof programs, or also work being done in Los Angeles right now with their cool streets, where they're really looking at the practicality of actually changing streets and the albedo of streets and the cost and the benefit to that. Albedo strategies are really useful, especially for places that don't have a lot of rainfall, like Los Angeles. We can look at waste heat strategies and specifically bring in energy efficiency. We see a lot of waste heat from all the machines that are being used in our urban environment, a huge part from transportation sector, but also from everyone using all their air conditioning and as our main adaptation device during these extreme heat. But we can also look at vegetative strategies. And so vegetative strategies have shown to be one of the most effective strategies at reducing the urban heat-on effect in places with sufficient rainfall. And they've been shown to reduce the urban heat-on effect by as much as 50%. And so vegetative strategies can include green roofs, and we can look at Chicago's aggressive green roof policies that's linked to their FAR policies. And we can also look through urban forestation and the programs that big cities like New York and Los Angeles are doing to plant millions of trees within their urban environment, as well as all the great work that's being done in state agencies to actually support their urban forests by tracking them and managing them and maintaining them. And so all of this is great work that can go to making us more resilient to extreme heat. And so we see, this is an example of Paris. I was in Paris last year when they had their big heat wave at the end of June, and it was an experience to be there. I was there actually giving a talk on similar to this on extreme heat. And Paris, since it was so impacted by the heat waves and the European heat waves 2003 and 2006, they're really pushing really great policies to try to adapt and mitigate heat. And so Paris is bringing in huge mature trees into their urban environments in a way that they've never done before. And actually, it's interesting for me as an architect and urban designer to see that they're putting them in front of the Opera and the Hotel de Ville, of these iconic buildings that were designed to be open and have a beautiful vista. And so it's really interesting to see Paris begin to remake itself more as a green city. But they're also, having access. It's important that the public has access to green spaces to cool, but also to spraying and misting systems to cool people in these environments, but also just the presence of water actually cools the near surface air temperatures because of the process of evaporation. And so with the different strategies, I was really interested to look at the role that urban agriculture can play in lowering temperatures. And so this was some work that I did, was I looked at the role that urban agriculture can play as a heat mitigation strategy, specifically looking in the city of Atlanta. And so for this work, I looked at both the MSA level for Atlanta and then the city level. I included land cover data, and I used temperature data, satellite data that was specifically nighttime data. It was really important that I use nighttime data because, number one, as we talked about, the minimum temperatures have the stronger effect of heat mortality. But because I was interested in urban agriculture, I was hypothesizing that agriculture would have a greater potential than other green infrastructure strategies, such as tree canopy, at actually lowering nighttime temperatures. And so I really wanted to look at that, as well as look at the timing of how well do these green infrastructures perform during times of extreme heat. For the city level, I brought in urban form variables. And so like Heather was brought up earlier, we're working on doing local climate zone mapping for Bloomington and Indianapolis right now. And this is one of the reasons why, is so we can see and have a better understanding of how temperatures are changing. And so this was some of the local climate zone work and the urban form parameters I put into the analysis at the city level. At the MSA level, I found that agricultural lands actually outperform forested lands in reducing nighttime temperatures. And so there are different reasons why we would expect this. And one of the main reasons is that trees actually can trap temperatures at night because of their wonderful canopy that we use and rely on in the daytime that cools us in the day. So in no way is this work trying to say that trees are not good for helping us with extreme heat and heat waves, because they are, but it's a larger discussion to understand that maybe we have different strategies that we should look at when we're designing these type of green infrastructure strategies. Also, we found that if we increased 10 acres of agriculture within a 1 kilometer grid cell, that we saw that we could reduce approximately 10% of Atlanta's urban heat island. And so this is going to this understanding that we can start seeing some impact at this local level. Looking at it at the urban scale, I was really interested to see, number one, if we saw interaction effect between where we placed agriculture. So for example, if we place agriculture in a dense downtown area, do we see that it decreases temperatures more than if we place it in a residential area? And what I found in my initial analysis was that I didn't see an interaction effect, that the temperatures decreased, but there was no significant difference in the way they decreased unless I looked at the difference, whether a heat wave was occurring. And if a heat wave was occurring, we actually saw a difference in the reduction in temperature and greater temperature reductions in urban areas. And so heat wave was acting as an effect modifier. And I think this is a really important thing to bring up, because when we're designing for communities and green infrastructure, we need to make sure we understand how these strategies work during times of extreme heat. Because these are the times when we need them the most. I was really interested to see if we see the same amount of decrease in temperatures from agriculture during heat waves. And what I saw was that urban agriculture decreased temperatures less during a heat wave as compared to non-heat wave, but in retaining approximately 25% of its cooling potential. So it decreased temperatures less, but it still cooled temperatures, whereas forests actually started having a slightly positive effect on trees at night. And so this is, again, important with regarding this understanding of timing and the importance of heat waves. I was also interested to see how big of a land do we need. So if we're going to put urban agriculture in to reduce temperatures, where do we actually, can we just put a small parcel? Is that enough? Or do we need to see a sizable area? And so the work was teasing out that what we were seeing was approximately 7.5 acres were needed. We start seeing this almost threshold of effect happening around the 7.5, where we see decreases of temperatures happening at this 1 kilometer grid cell. And so this goes to this understanding that for policies, and this is one thing I want to bring up with how do we make our communities resilient and prepare for extreme heat, is that we really need to design targeted policies. And so targeted policies to actually address these conditions. So one thing is that we see with agriculture, one of the biggest cooling benefits is that it's often irrigated, and that is that presence of water that helps, but it also has to do with different parameters of, like, there's stomatal resistance that impacts their cooling potential. And so it's really important that during heat waves that we're actively managing our green infrastructure, and specifically our urban agriculture. And this is a hard question during extreme heat, because usually this is hand in hand with droughts. And so communities are going to have to make these tough decisions of how do we decide to use our water, and water is a scarce commodity. And so I don't have a clear answer there, but this is one of those discussions I want to help contribute to, that if we do want our green infrastructure to help cool us during these times, there needs to be some active management for them. Also, the location of agriculture matters. So urban, if we should keep urban agriculture urban. And so we see a bigger effect during heat waves if we put agriculture into downtown areas as compared to residential areas. And those were the two, actually, the local climate zones we compared with those two. And so this might be going in the face of some policies in some cities who are really pushing to support urban agriculture. But Philadelphia's zoning ordinance, for example, doesn't allow commercial agriculture or market or community supported farms in the downtown area. And so there might be good reasons for that. But again, this might be losing the opportunity for agriculture to be able to cool these places. And then size matters. And so the largest, like we saw, about 7.5 acres are needed to start seeing a decrease in temperatures at this 1 kilometer scale. But the largest farms in the US are around 5 to 6 acres. There's not a ton of them that are that large. And so we really need to be thinking about how we can leverage public land. And so Park Pride in Atlanta is a good example of how they're leveraging park space in order to turn that into agriculture space. Or Philadelphia has an interesting vacant toolkit. So this brings me to another study that we did, which was a climate modeling that looking at specific. And so what we were interested in seeing is, can we save, if we project climate out to 2050, then can our climate responsive designs cool temperatures out to 2050? And so what we did was, we were really interested to see, for example, with these climate adaptation strategies, was that, say, for example, if you paint all the roofs in a city white, how would that impact climate? Or if you put trees in all the available space, how would that impact climate? And so we looked at this at 3 different cities. We looked at Atlanta, Philadelphia, and Phoenix. We looked at their population change and used that for projections up to 2050. We did the climate modeling through WRF, so we used the regional climate model of WRF to do our climate models. We actually also looked at land cover and looked at how land cover has been changing and projecting that out to 2050 as well as an input into our model. And so we developed these different climate scenarios, and the climate scenarios were pretty much based on a greening scenario, an albedo scenario, and then a combination of the 2. And for the greening and the albedo scenario, we designed the policies so that they would target either public land or private land, because we were really looking at policies that would be implemented and enacted for parcel level development. And so policies that cities could use through zoning ordinances or different policy approaches. And so we put this into a health effects model called BINMAP to also model the effect of the prediction of mortality that would result from different climate factors. And so we see from the analysis that this is showing the difference between business as usual conditions. And so and these are grouped by the different policies and the different cities. And so we can see that these are decreasing in different ways in the different cities, but for the most part decreasing. And then we can look at this with regard to mortality and look at this is looking at the differences in death. And we can look at how many lives can we save with these type of climate adaptation policies. And so with the policies, what we found was that places like Phoenix, it was the albedo strategies that worked better in Phoenix than, say, the vegetative or the combined. And that makes sense because Phoenix is a very dry and arid place, and so the albedo enhancement policies are going to be better suited for a place like that. Whereas in Atlanta, we see that the combination of the 2, of the greening and the albedo, have the biggest impact, and that with when bringing everything together in Atlanta, we could almost reverse the impact from climate change, and we could save a large, almost like 80 to 85% of lives that would have been lost. And so this really gets that understanding our location. So when designing policies, we need to really understand which policies work for our region, our location. But one thing that we also did in the study, which I wanted to discuss here, was that we looked at the distribution of environmental health benefits from these different climate adaptation scenarios. And we looked at with regard to the distribution, with regard to the age of the residents in the cities, the median income, and then the race. And we wanted to see if we saw differences between these variables, that if we put these climate adaptation scenarios in areas of very poor areas, do we save more lives? And if we put them in areas that are wealthier, or if we put them in places that are more predominantly white versus one that are areas are non-white. And so we actually see that we can save more lives if we target our policies to areas, especially for Atlanta. Atlanta was in my opinion, the clear one here, where we actually see that we can save more lives if we target our strategies in areas of income, of low income, as well as with regard to race. And this is, I think, on everyone's mind right now. I feel like we're having these larger discussion of looking at systemic racism in our communities, in our cities. And I wanted to bring up this wonderful New York Times article that I'm sure most of you had seen, that was released in August of this year, that really was illustrating the great series of works that have been released recently on tying redlining, historical redlining of communities of the past, to the fact that we're still seeing the effects of that systemic racism, and that within these red light communities, we see less green infrastructure, and we also see that these are areas of that have the highest temperature. So I wanted to point another image that comes from the New York Times article, Atlanta here. And so we see areas that were A-graded areas as cooler than areas that were D-graded, which were much hotter. And so I think that this, again, brings up this importance with regard to policy, and that not only should we be targeting policies with regard to how can things reduce temperatures the most, or how large should green infrastructure be, but also where we can actually save lives the most, and where our most vulnerable populations are located in our communities. And I think that's an important discussion for cities and communities to be able to protect those and the most vulnerable. And so what we see with vulnerable populations is that we see that that age has a huge impact to vulnerability to extreme heat. The very old, the very young are very vulnerable to extreme heat. We're actually seeing more focus on extreme athletes and how they're becoming more vulnerable to heat by performing their high performance in these extreme heat conditions. And that we're even seeing this down to high school football players and college football, and an increase of deaths from heat strokes to these athletes, to the point that it got brought up for Congress, something to be discussed and dealt with. And so for communities, when preparing for extreme heat, we should know where our vulnerable populations are. So we should be looking at this with regard to age and income, but also isolation. Isolation is a huge variable with regard to vulnerability to extreme heat, especially the elderly living alone. Access to air conditioning is really important, because we see that air conditioning is our main source of adaptation during these times of extreme heat, as well as income, which those two can go hand in hand. Pre-existing health conditions such as diabetes, cardiovascular disease, and respiratory diseases all show that increases a person's risk to extreme heat events. And so these are vulnerable population characteristics that communities should understand and really be targeted in their communities, as well as understanding exposure. So not only who's more vulnerable, but who's being exposed to higher temperatures. Very similar to what the New York Times article is showing, the researchers looking at redlining and the correlation of temperatures and infrastructure. But areas with high impervious surfaces and lack of green space, housing conditions, and lack of transportation, these are all things that can increase our exposures to extreme heat. I love this quote by a researcher in Chicago. It says, "We need to better understand where the most vulnerable people are in order to get to them quickly and to reduce their vulnerability over time through planning." And so it's both the immediate reaction that we need to be thinking about in extreme heat, as well as how can we increase the resilience over time. I want to bring up some work that I did on sea level rise on the Georgia coast, with specifically talking about vulnerable population. So we looked at the impact of sea level rise with regard to physical geographies and social geographies, and on the Georgia coast. But with social geographies, we're looking at social vulnerable populations. And we worked directly with the Gullah Geechee. And the Gullah Geechee is one of the most intact African cultures that we have in the United States, with direct ties to West Africa. And their community lives and is distributed from the Carolinas down to Georgia and North Florida. And these communities are often located on islands on the Georgia coast. For example, we were working with ones off of Sapelo Island, communities of Sapelo Island. And with sea level rise, we're going to see a huge impact to these communities because of them having to retreat on land. And if they are retreating on land, what is going to happen to this very important and very rich culture that might be lost? And so when we're thinking about vulnerable population, I want us to think about the demographics and the exposures, but also the importance for heritage and culture that could be displaced and lost due to these changing climate. So I'm going to wrap up by talking about some work that I'm doing in smart cities and environmental sensing. And so When I talk about environmental sensing in smart cities, I always bring up the question of why sensors? Why do we need sensors to do to really look at extreme heat? And so one reason, as I've talked about in the lectures, that we see that temperatures vary dramatically within a city due to the urban heat island effect. But most cities are only quantified by one meteorological station for their location for their region, which is normally located at an airport. And one meteorological station just is not sufficient to be able to depict the temperature variation in an urban area. And so researchers use satellite data a lot, which is very useful. And but satellite data also has its limitation due to its spatial scale as well as its temporal resolution. And so that is one reason, as well as the fact that satellite data is capturing surface temperature and not capturing near surface air temperature. And it's the near surface air temperature, specifically at 2 meters, which is that's the best to associate with negative health effects. So for us to really tie this to health effects, we really need that 2 meter and that distributed into the environment. So this is why we're seeing this push towards low cost ubiquitous sensing in our urban environments, is for these different ways as a way to improve our understanding of exposures to high temperatures, as well as to better quantify these different climate responsive designs. And so Chicago Array, we've seen sensor networks pop up in different areas in the United States, and Chicago Array, I think, is the most prominent one, where we're seeing, around 40 to 80 or 100 sensors, I think, now at this point, but plans of installing up to 500. So the most, I think, well-established one, sensor network, where they're using what they're calling these modules that are capturing way more than just temperature data, but a series of environmental data as well as sound and video data. And this brings me to some of the work that I'm doing here on Bloomington IU campus, is where I'm putting sensors onto IU campus to start monitoring how temperatures are changing in the urban environment. And I've also put sensors into different locations of urban agriculture in Bloomington to look at temperature and relative humidity, but also to monitor soil moistures and to really start trying to investigate the impact of soil moistures on temperatures as well when looking at agriculture. And so these are some of our sensor systems that we have deployed campus and in Bloomington. And so a simple visualization that I can show is that when looking at just 3 of these sensors and looking at them, let's say in a parking lot and a forest area and in a community garden, we see that the orange is the parking lot, and it's the hottest one that we see in day and night. And so we can see that the temperatures increase here in the daytime and then come down at night. And so we're seeing these diurnal temperature trends here with this graph. But we can see that the temperatures in the parking lots are the hottest, and then actually the coolest in the daytime by a significant amount is those located specifically, this is a Dunwood sensor, so what's located in Dunwoods, and that the community garden is in the middle. But we see this flip-flop here, which is what my research previously was showing, that it's actually, agriculture actually cools temperatures better at night than forest, and so we see this flip-flop between forest and agriculture. So it's nice to be able to really tease out these impacts of temperature, and not just at one point, but really thinking about the diurnal temperatures and changes in an urban environment, and the importance that minimum temperatures plays for our communities. And so with this is I've got ongoing and new projects. And so this work is being funded by the National Science Foundation through the CRY program. And so where I am putting both these in situ sensors, like I explained earlier, as well as on-body sensors to look at heat exposure. And so with the on-body sensors, we're monitoring individuals' heat exposure. We want to monitor individuals' heat exposures. And we're really looking at this for validating wearable sensors. We're really interested to see, can sensors, if we wear them on our bodies, really be able to capture heat exposure, because that would be fabulous if we could get that data. And we're starting to see a lot of research that is starting to use that, because these are really important for putting on vulnerable populations and seeing their exposures throughout the day. And then we'll be moving into really thinking about personal heat response, which is really thinking about how our body responds to heat, not necessarily how our exposure. And so we ended up having 4 different sensors that we use, and we put them all over our body based on the literature to see how they perform in different environments, specifically looking at Dunwoods and Luddy parking lot and see how well they perform. And what we found from this research is that the sensors actually are not performing very well, that they're actually overheating, especially in areas of high impervious surface, as well as in direct sunlight. And so this is really a push that this is an important technology, that we could really use this for vulnerable populations and for communities, urban communities with changing climate. And this could be an important area for intervention in order to capture heat exposure. And so with my sensor network, I've been working on a series of different projects and really thinking of how can we use sensor networks to help stakeholders and communities. We can definitely use sensor networks to improve our methodology and to understand urban climatology better and heat wave trends, and which is very important. But we can also look at it through looking at and quantifying green infrastructure performance during times of extreme heat, maybe tying that into smart irrigation and water harvesting so that we are harvesting and protecting our green infrastructure. We could use it for building energy and the role of looking at building energy modeling, as well as a potential for emergency response. And so that's one of the things that we're wanting to be working on in the near future is how can we really depict how temperatures are changing our urban environments, and how can we give this information to people in their built environment so that people have a better understanding of their hyperlocal heat exposure when they're moving and through an urban environment. And then another project that we're working on now is actually looking at building energy use with regard to green infrastructure and trying to see specifically on campus if we see that buildings use less energy if they're surrounding by different types of green infrastructure. And so that's work that we're just really starting to really delve into, and the role of sensor deployments could really enhance this work to really understanding the correlation of the near surface air temperature outside of buildings. And then one that I'm very interested in is really this emergency response, and how can we tailor emergency response to vulnerable population mapping with sensor networks, so that, as the researcher said in Chicago, how can we get people an emergency response to people when they need it at that time? So that wraps me up for my my talk. As we really want to talk through how we can empower and protect our communities. And so I went through talking about heat wave trends, and it's important for communities to be able to really assess their heat wave trends and their vulnerability to extreme heat, looking at different climate adaptation strategies and the role of that, and that when we're designing policies, that we should be designing targeted policies to make sure that we're getting the best bang for our buck, but also that we're actually putting policies in places where vulnerable population and disadvantaged communities, and those that are most vulnerable in our communities, are located. And then a discussion on sensing technology and how sensing technology can help us to better be prepared. So thank you very much.
Thank you. Adam, I don't know, are we supposed to unmute everybody, or do you want me to?
No, you can, you'll ask the questions.
Okay. Great. Well, Dana, thank you. I'm clapping vigorously on behalf of the whole crowd, I'm sure, because that was a fantastic.
Let me mention real quick that if folks have questions that they haven't asked yet, they can type them into the chat now.
Thanks, Adam. And yes, Dana, that was a fantastic talk. Really wide-ranging but cohesive talk that really gives us an excellent view of so many of the different complexities, policy issues involved in thinking about how to keep our cities cool. So that was really enjoyable. We do have a first question that came in early on in the talk when you were talking about, excuse me, your comparison of cities with respect to their vulnerability. So the vulnerable cities analysis. And the question is, have you compared vulnerable versus non-vulnerable cities from the vulnerability analysis to see if there are any trends with local zoning, ordinances, or other policies that contributed to whether a city was vulnerable or not? Or do you think that cities being vulnerable or not is totally a consequence of geography and natural features?
So that's a great question. So I didn't talk about this enough, but that's where our future work for this study is going to go, is really look at the difference between minimum and maximum temperatures. And we have work that I worked with on the Urban Climate Lab back at Georgia Tech. We have done trends analysis for urban heat island trends. And so we really want to correlate how quickly cities are increasing their urban heat islands with heat wave trends. And if we see that places that have large growing urban heat islands are correlating with places with increasing heat wave trends, then we want to try to start teasing that out with regard to development policies, and with regard to lack of green infrastructure and increase in repurposed surface and increase of population growth and sprawling of communities, because we see a direct relationship between sprawl and urban heat islands as well. So that's a great discussion to really, that's where we really kind of want to tease that out more to see, how our cities becoming more resilient because they have better strategies for design and development.
Thank you. Okay, another question. How do you determine heat wave season for a particular location?
So we don't define the heat wave season. So we let the data tell it to us. So we define it by when the heat wave starts and where the heat wave ends. And so then we look at the start of the first heat wave, and then we calculate the time to the time of the last heat wave. And then we look at how heat waves are increasing earlier in the year, as well as how they're lasting longer in the year. And that's that we're looking at. So we don't say heat wave season is May 1st. Instead, we're saying, no, the heat wave season is actually expanding and changing in these areas based on the fact of it's not just when the first extreme heat event is, but when the first heat wave is.
Okay, thank you. Another question on COVID and heat waves. You mentioned that those most vulnerable to heat waves are the elderly, the isolated, etc. This is similar to who is most vulnerable to COVID. What can we learn through this pandemic on helping those vulnerable to heat?
That's such a great question. I actually spoke with a media outlet about this summer. There's a lot of correlations between extreme heat mortality, extreme heat vulnerability, and COVID. And so looking at pre-existing conditions, the elderly, all to make people more vulnerable. And so things that we can expect, things that become problematic during times of extreme heat is the fact that if we have power outages and people need to get to cooling centers, just like we see with what's happening with the hurricanes, how we shelter in place together can become more problematic. People can't just go as easily to the library and cool themselves down because it's a hot day, because the library is closed and not allowing people in. And so these normal public infrastructure that are cooling centers for people, especially people that don't have air conditioning, become really important. But also one thing that I thought was really interesting between the link between COVID and extreme heat is this understanding of how people started really reaching out to their elders during times of COVID. Let me go shopping for you. Do you need something? And what we see is that this type of check-in is really very effective for the elderly and for saving lives. And so the two historical heat waves that people talk about in the US are the heat waves in 1995 and 99. And these heat waves are very similar characteristics, of meteorological characteristics. But in 99, they saved a lot more lives. And one reason is, again, the community's more prepared. And one way they're more prepared was because they did knocking on door campaigns of going to check in on the elderly who were isolated. And I think was something that was really beautiful to see in COVID, where communities really not asking for someone to ask for help, but instead asking people, how can I help you? And I think this is a mentality that we need to maintain and support, of how we can continue this type of check-in and support for our most vulnerable during these times where, going outside is the exposure. Great question. I feel like I could talk about that all day.
Another question that came in, another interesting characteristic looking across cities is that some, like San Francisco, don't have a robust network of centralized air conditioning due to historically not needing this, while others, like Austin, already have more widespread access to residential air conditioning. Do you think that there will be positive feedback in those cities without current air conditioning networks? As they're installed, this will accelerate their heat wave extremes faster than other cities with this already built in.
So we definitely see this problem with housing condition. And so when we're thinking about housing condition, you know, you can think about insulation, people who live in trailer homes are going to be way more vulnerable as well. So housing condition is really important. The area around the housing is really important for increased exposure, but access to air conditioning is extremely important. And so what we're seeing is not just access. So access is really important for places like San Francisco and Paris. So you go to Paris and most those buildings did not have AC. And so it is very difficult to be inside of a building in Paris during a heat wave. It's very dangerous. And so that's a really important question of how do we transition these communities because for the most part, San Francisco, people that live in San Francisco was like, I'm not going to pay all that money for an AC when I only need it like a week of the summer. And so there is this built-in vulnerability that they're not prepared for this. And so hopefully this leads to that discussion that these housing conditions do need to be upgraded and we do need the access to air conditioning. And it is this wonderful question as that, again, just like watering agriculture, there is always a double-edged sword here that using air conditioning is going to be using more energy, that's going to be increasing waste heat, that's going to be increasing climate change. So there's not just a simple solution here, but we can think about energy efficiency. We can think about where that energy is being sourced. We can think about the fact that as well, not just access, but the ability to pay for AC and for air conditioning. A lot of low income communities go without AC because they can't afford those high bills. So that's an important aspect of what as well, or if their air conditioning breaks in the middle of the summer, being able to just, you know, and have that money to fix it. And I was literally writing an NSF grant this summer all about this work, and my air conditioning broke. And it took so long to fix it in the middle of a heat wave, and we couldn't go anywhere because of COVID. And I was sitting there writing about vulnerable populations. It was like my method. I felt it was my method way of actually writing a grant. But it really, you know, illustrates to me at that moment as well. But it's expensive to even fix our air conditioning unit. So there is this importance that when you think about with housing stocks, the healthiness of our housing stocks, but as well as income and the ability to be able to afford and have access to air conditioning.
Do we see a measurable heat island effect in a town as small as Bloomington?
Yes, we would see one. I haven't actually calculated it here in Bloomington. That should be something I do the next little bit because I do get asked that a lot. But we are already seeing that, you know, these differences in microclimates. But what we might not be seeing is that they're not going to be as intense as we see if we were studying this in Indianapolis or in Chicago. We might not see this increase in the trends that we're seeing as clearly as we see in these larger cities. But we still see this distinction between this urban and the rural here. And so that's a great question of knowing at what level do we see that impact. But the work that we were showing before the trends was really looking at large cities and saying no matter where they're located, they should. And I think that we could do another analysis looking at smaller tiered cities as well. Look at their trends across the United States to see, yes, these cities, and make that argument that these cities are as vulnerable as well. And I think that would be an interesting thing to dissect.
Okay, and this is going to be the last question because I actually have to go to another Zoom at 1 o'clock. The question is, for cities with heat monitoring networks, what's the recommended geographic distribution? How far apart should sensors be?
So that's a good question. That's something we're trying to figure out right now. So right now, the density that we have in our network on campus is, and I can't remember what it is off the top of my head. It's you know, definitely less than a kilometer a sensor, and it's at least double that. And that was around the recommendation. I still think that is something we are trying to figure out as we're going to be testing how we can effectively map temperatures in urban environments by using these sensors. And so one of those questions are going to be, how closely do they need to be located to each other to be able to get these valid temperature readings, as well as what's the density of them. So that work is starting to come out. And I think that's a great question to ask, of what's not just how far, but what's the density of the sensors as well. And that's something that we're currently investigating.
All right. Well, thank you on behalf of, or I'm thanking on behalf of, you know what I'm trying to say. I thank for the whole crowd. This was a fantastic seminar, and really enjoyed it.
Thank you.
Good luck.
Thank you, Dana.
You're welcome.